good afternoon, everyone. I have to say that I'm very honored to be here among this list of very distinguished guests, obviously. And I would like very much to thank the organizer, and especially Jean-Michel Raymond and Nicolas Treps for having invited me. The thing I don't thank them for is to have put me in the program just after my former PhD advisor, Alain, because now I feel the weight of all the giants on my shoulders. So. On top of that, I have to also make a confession here, which is that I am the one who dismantled Alain's experiment in the lab because I needed some space when I took over the lab where he built his experiments. So I was trying to kill the father in a sense. Right, so what I've been asked to do is to discuss about some recent experiments where all the concepts that we've learned today, since the talk of Serge Haroche in particular, and also the talk of Alain, so all the concepts that have been discussed. So basically I will discuss recent experiments on interacting Rydberg atoms where the concepts also introduced by Bohr are very useful. And the title is then a toy many-body system, and what I should try to explain you first obviously is what do I mean by this toy many-body system. As you very well know, in the last century we've made huge progress in the understanding of the microscopic world. Obviously, we understand very much in great details the interaction between atoms, between molecules. We even understand that at a deeper level in high energy physics. But on the other hand, on the other scale actually, we also understand pretty much the macroscopic world. I mean, we've got thermodynamics, we've got laws of classical physics, which actually rules lots of objects around us. And the big issue at the moment is how do we bridge the gap between those two huge scales. So there is basically the few particle scales, and there is this gigantic object composed of 10 to the 23 particles. So it's not because we understand very much the law, the underlying law of the system, that we necessarily know how to go from these laws of microscopic world to the laws of the macroscopic world. Some people say, well, why caring? Actually, each stage of the ladder, of the scale, will have its own different law, and maybe it's not necessary to try to bridge the gap. Nevertheless, I think that most of us as physicists have deeply rooted in our genes this idea of reductionism, which is the fact that we can go from the microscopic laws to the upper scales. And so maybe that's the reason why people are still trying to build some toy model that will explain you, to try to, in a sense, trying to make the emergence of complexity out of the laws of the microscopic world. The notion which is, the concept which is very important here is the concept of complexity. And so obviously we all know that, even from the classical point of view, but in the quantum world it's even more striking. Because for example, if you take an ensemble of two-level systems, we know very much that the size of the Hilbert space has an exponential scaling with respect to the number of particles involved. And the consequence of that is that already when we have to handle an ensemble of about 30 or 40 particles, which is not a lot if you compare that to the 10 to the 23 particles that you have here, we don't even know how to do any ab initio calculations, despite the fact that, once again, we understand very much and in great details the underlying laws. So that's, in a sense, the prime of the many-body physics to a certain extent. And one idea is to follow a suggestion by Feynman in 1982 that Alain just developed a minute ago, which is to say, why not trying to engineer in the lab some quantum system, measure the properties of this quantum system to try to answer certain type of questions. So it looks completely trivial, but it's not actually, because usually what we do, especially as experimentalists, but also generally as physicists, we just take a system that we have in front of us and we do measurement on it. From this system, what we do, we try to idealize and find kind of the Hamiltonian that describes the system. Here, that's not what I'm doing. I'm thinking of a Hamiltonian, whatever it is, and I try to engineer in the lab kind of another system, which I hope is not too far from an ideal system I'm trying to simulate. Okay, so that's a bit what we're trying to do here, is to reverse the order of that people have used so far by engineering, by thinking of an Hamiltonian and engineering in the lab. And we can do that thanks to the advances in technology. I will show you examples in a minute, some kind of artificial system that we can study and try to find if this system that we are studying exhibit, for example, superconductivity or any other useful application that I will detail now. So, among all those implications of this quantum state engineering are the following one. So, there is exactly what I just said a minute ago. So, the problem of many-body systems, you just take a piece of superconductor, for example, high TC superconductor. We still don't really know how it works and what is the underlying mechanism responsible for superconductivity in ITC compound. But still, we could engineer in the lab some kind of ideal system that maybe would feature this superconductivity. So, that's one example. Another example is the field of quantum metrology, which is the idea that if you use entangled state, what we've just heard about, it's possible to do measurements that are much more precise than measurements that we do usually. So as you all know, for example, time is defined the second is defined from a transition in cesium atoms. It turns out that if you take a collection of n cesium atoms, and that these n cesium atoms are not prepared as a collection of independent atoms, but as an entangled state, you can enhance the precision of your clock by a factor square root of n. So if you take 10 to the, let's say, 8 atoms, you immediately gain a factor 10 to the 4 in the precision of the clock. So it can be, this quantum engineering has the potential to really be kind of a revolution in measurement, in high precision measurement. There is also another application, which Alain described as well, which is quantum information, which basically has two aspects. The first aspect is the quantum communication, so to use some kind of correlation, quantum correlation like entanglement in the systems to perform some secure communications between two partners, so usually Alice and Bob. That's one side and one aspect of quantum information, but there is another one, which is quantum calculation, quantum computation, where we could also make use of entanglement to try to calculate in a much more efficient way than we can with classical computers some particular task like searching within a list or factoring numbers. So this is this idea that you change exactly what Alain said, the class of complexity of a system from something which, for example, has an exponential scaling to something that has a polynomial scaling. So basically a classical computer would have a very hard time to handle this kind of complexity. A quantum computer would be able to handle the complexity because it changes the classes of complexity. And now there is also something that we've heard a lot about this morning, which was this idea of the transition between the quantum and the classical world. So whether there is such a transition, whether there is a smooth connection between quantum and classical through decoherence, as was discussed by Serge Haroche this morning. And I think it's still to a large extent, an open question. So, as I said, the reason why we can now do this kind of quantum engineering is because of the very impressive progresses that have been done in the last 20 or 30 years in various labs around the world in manipulating individual quantum systems. So that's essentially what I'm going to talk about today. So as also Alain has discussed a bit, and obviously Serge Haroche this morning, there is some kind of system like trap-cold ions, where basically we can trap and manipulate individual ions and create some kind of entangled state. You also have the system that you all recognize from this morning's talks, which is controlling the interaction between atoms and photons through, for example, a high finesse cavity, and the atoms can go through and interact with the photons. And there is what I'm going to focus on today, so those cold atoms, so laser atoms that have been laser cooled, so extremely cold, and that we can also manipulate. I will say obviously a bit more later. Since about 15 to 20 years, there is also a new class of systems that people know how to engineer in the labs and that are completely fascinating because despite the fact that they contain a huge number of particles, so typically 10 to the 20 particles, I mean those are microscopic size objects, still they behave like a kind of a simple ion or a simple cold atoms. They contain a huge number of atoms, but the number of degrees of freedom that you can isolate make them look like a two-level system, for example. So this is an example of a superconducting circuit. I've taken this picture from the group of Daniel Estève in CEA, in Saclay. There are also some examples of NV centers, so basically this kind of system looks like an artificial atom as well. So the basic idea of all these systems is that you can use them to construct in the lab many-body toy systems. So among all those systems, the one I'm going to concentrate on is the case of cold atoms, and in particular cold atoms that we've been introduced to this morning by Serge Haroche. So this is the outline of what I plan to cover. So first I will do a brief reminder of Rydberg atoms. We've heard a lot about that this morning, but I will be a bit more specific about what I will really need during this talk. And in particular, I will take a bit of time to discuss the interactions between those Rydberg atoms. And one consequence of these very strong interactions between Rydberg atoms that I will discuss is what is called a River Blockade that immediately projects us in the world of many-body physics. So I will spend a bit of time trying to explain you what is the River Blockade, and then I will move on to a recent experiments that have been done either in our lab or in the US to demonstrate at the two-atom level, this blockade, so it will show you kind of the state of the art of the manipulation of the interactions between two atoms for this, using this Rydberg interaction. And then I will move on some kind of more complicated many-body system and look at the River Blockade now in ensembles of 10 to the 6, 10 to the 8 particles. So there is a huge gap that for the moment hasn't even been bridged. So I'm not talking about the gap between a few and 10 to the 23, I'm even talking about the gap between 2 and 10 to the 6, for example. So even that, we are working in trying to control these interactions at this intermediate scale. And finally, I will show you two examples that I find pretty nice of the Rydberg blockades in quantum optics, trying in particular to use these very strong interactions between the atoms to make two photons interact, which looks kind of bizarre. That's using a nonlinearity which acts at a single atom level, single photon level. Sorry. So let's start by the Rydberg interaction. So we've all heard this morning about Rydberg atoms. So a Rydberg atoms for me and for many people actually is an atom for which the outer electron, so I'm just taking the case of the first column of the periodic table, so for me an atom will only have one external electron, is very far from the nucleus. There is a difference though with respect to the Rydberg atoms that Serge Haroche discussed this morning. The one I'm going to discuss have usually very low angular momentum. So they are not circular Rydberg state, they are kind of elongated. So they look a bit like that. And in particular, the electron can probe the electronic core of the atom. So quantum mechanically what this means, obviously, those are states that are very close to the ionization threshold of the atom. So typically, principal quantum number much larger than 1. All right, so as Serge explained us this morning, in this case, we can define, all the degrees of freedom of the electron and of the atoms. They essentially look hydrogenoid, and therefore, the energies are scattered following this formula here, which is the usual formula that we use for the hydrogen atom, apart from the fact that there is a very slight correction here, which is that instead of taking the full principal quantum number n, I slightly correct it by the possibility, and that takes into account the possibility of for the electron to go inside the electronic core. So basically, I don't have the full screening effect because they have low angular momentum, so they could fill the electronic core. But for the rest of the discussion, I will completely forget about this tiny difference with respect to Serge Haroche things, and mainly say that this is the principal quantum number that governs the properties. So now we come to a kind of classical, semi-classical argument introduced by Bohr actually. So in the Bohr model, one very striking feature of this atom is their huge size. So typically if you apply the Bohr model, what you find is that the radius of the atom, which is to say the radius of the orbit of the electron around the nucleus, scales like the square of the principal quantum number. But so now, if you take a principal quantum number which is around 50, as I will show you we do in the experiment, you see immediately that the size of the atom is gigantic. So it's not one Bohr radius, so A naught, it's actually 3,000 times larger than that. So the electron is about 100 nanometers away from the nucleus. Okay, but this has several consequences, and in particular we developed 3 of them that will be very helpful and useful in the rest of the talk. The first one is the fact that because the electron is so far from the nucleus, classically they develop a huge dipole. And the scale of this dipole as well scales like the principal quantum number square. So basically, if I have 2 states NL and N prime L plus or minus 1, I need to change the parity in order to have a non-zero dipole, then I find that the dipole element is just the square of scales like the square of the principal quantum number. So what it means is that immediately I see that there will be a huge dipole-dipole interaction for those atoms. I will obviously say more in a minute. So an example is again for n equal around 50. This dipole matrix element is 3,000 times larger than the dipole moment of a molecule which is already considered as very polar by chemists, which is water. So you see that immediately we are having a control on the interaction, which is on the dipole of the particle, which is impressive. Second byproduct of the fact that the electron is very far from the nucleus, it's the fact that it's an extremely polarizable particle. And in particular, it will be very sensitive to any static or AC electric field through the Stark shift, obviously. So you can use that as an asset in order to manipulate the interaction energy between the atoms. You apply the electric field, you polarize the dipoles, and so on. So once again, scaling is pretty wild. This is an n to the power 7. And I will show you in a minute an even wider scaling when it comes to the interaction energy. And the last thing that I will use, and Serge actually already discussed that this morning, is the fact that they have very long lifetimes. So typically for the kind of states that we're using, this lifetime scales like the cube of the principal quantum number. All those scaling, by the way, could be rederived using the Bohr model that we are actually discussing today. So, as an example, if you take n, the principal quantum number, larger than 660, typically the lifetime of the atom is about 100 microseconds, which is a huge at an atomic time scale, because typically this is more on the order of 10 nanoseconds. So basically, for everything that I'm going to report today, this is an infinite lifetime. The experiments will be done much faster. All right, so now let's discuss the consequence of the large dipole at the level of the interaction energy between the particles. So as you know, I have two neutral particles, so they interact not through the Coulomb charge, but they interact via the second order Coulomb interaction, which is the dipole interaction. So basically, the interaction that governs this is the usual dipole-dipole interaction, dA.dB over R cube. Here, this is the Hamiltonian, so dA and dB are the operators. So now if I want to understand the system, I need to work in the 2 atom bases. So basically, I specify the principal quantum number for the first atom, tensor product of the principal number of the second atom. Okay, and so now what I'm going to show you is that how we can think of the interaction energy between this particle and see the various scaling, which is something that most of you know, but I mean, sometimes people don't realize that there is actually not either a 1 over R6 or 1 over R cube dependency. It's actually a crossover between 2 different scaling. So let's assume that I want to measure or to calculate the interaction energy of 2 atoms, each of them being in the same Rydberg state NS. Now I can look at many other states in this 2 atom system, and in particular for most atoms I will find that there is one which is nearby, an NP and an N-1P. The exact states are not important, it's just you need to realize that close by there is a second state which describes this 2 atom system. And these 2 states are coupled by precisely this dipole-dipole interaction. Then now it is actually rather simple. The Hamiltonian reduced to this only pair of states. Once again, each state being a 2 atom state, then I have a 2 by 2 matrix with the coupling, which is the dipole coupling, and with an energy offset, which is delta. So now we have just to diagonalize this 2 by 2 matrix, and there are 2 extreme cases to be considered. The first case is the case where this mismatch in energy delta here is much larger than the off-order element, sorry. And so in this case, for which this is the interaction strength, the matrix element is much smaller than this detuning here, then the interaction energy is at the second order perturbation theory, which gives you the C6 over R6 law that we all know, which is the van der Waals law. Okay? But now, There is a second case to be considered. This second case is the case where in an opposite way, this detuning here is almost zero, in which case this is a 1 over R cube. The eigenenergies of this 2 by 2 matrix are plus or minus the off-order diagonal elements. So you see that just by varying the distance, it's not a universal law that actually you always have 1 over R6. That's not true. At very long distance, they always interact via a van der Waals interaction, and if you bring them close to each other, it will be a 1 over R cube interaction. And actually, if you do the scaling, once again using the Bohr model, you find out that this C6 coefficient in the case of the van der Waals interaction scales like n to the power 11. I don't know very many physics laws that vary so widely with a parameter, and this is one of these laws. So if you just change by a factor 2 the principal quantum number, going from 20 to 40, which is very easy with a laser, you tune the interaction energy over almost 10 orders of magnitude. So it's completely violent. So I will show you, obviously, that we see this kind of thing in the lab. All right. Now there is another knob. So now I'm going to make use of the fact that the atoms being highly polarizable, then they can, I can adjust the energy using an electric field. So basically, I can stark shift those various states here and bring this one in coincidence. This is called a first resonance, in which case for any distance between the particle, I will always have a 1 over R cube dependency. So this is a knob that you have in the lab to control the interaction energy between the atoms. This is an electric field. So this is, for example, the kind of situation where I plotted here the energy as a function of the electric field, and I vary this electric field. When I'm just sitting on resonance here for this particular electric field, this state is in coincidence with this one, in which case I have exactly the C3 over R3 interaction energy. So you see that it's actually much richer than just saying that the interaction between two atoms is just a C6 over R6. I mean, it's actually more subtle than that. All right, so now this was kind of a toy model to try to understand the interaction energy. At the end of the day, this is what it looks like in real life. So that's something our PhD students, Luca, has calculated for his thesis, which is the interaction energy for two Rydberg atoms, both of them located in the state 62 D3R. So you've got lots of quantum numbers to be given, but you see that there are many potential curves, and at the end of the day, if you scale this, you find that at long distance it's indeed a 1 over R6, and at short distance it becomes a 1 over R cube, energy scaling. So the bottom line of all that is that this Rydberg interaction is a very neat thing, because you can vary it over orders of magnitude, typically 11 orders of magnitude with respect to the ground state of the, when the two atoms are in the ground state. And that's also an interaction which you can switch on and off either by using an electric field or just by exciting or not the atoms to the ground state, to the Rydberg state. All right, so now I want to discuss two early experiments that were done using the Rydberg interaction, and there is one which two members of this audience are very familiar with, so Serge Haroche and Jean-Michel Raymond. So that was the first time, I think, that people have seen a clear evidence of this interaction between Rydberg atoms. So what they were doing at the time was the following. They were using a dense beam of cesium atoms. Cesium is one alkali as well from the first periodic, first column of the periodic table. And what they observe is just by trying to excite the atoms to the Rydberg state, they observe a huge broadening of the line when they try to increase the density of the beam, which is to say that they try to make the Rydberg atoms close and close to each other. In which case, the kind of broadening that they were getting was something as large as 10 gigahertz. So it maybe doesn't tell you too much in this energy scale, but what you have to report it to is to compare that with the temperature, in a sense. So basically, if you want a system where the interaction energy is the leading parameter, which is to say the largest parameter, you need the temperature of the system to be much colder than the interaction energy. And so that's the reason why, if you want a system which is fully governed by the interactions, people were moving towards colder and colder atoms, so that at the end of the day, the temperature is not at all a relevant scale. So for any practical purposes, you can assume this system has zero temperature. Okay, so the second kind of experiment that I want to discuss was actually one of the very first one which has been done with cold atoms. So it was in 1998. It was done not far from here as well, from Laboratoire Mécoton by Pierre Pillet and co-workers. And the idea was the following. So they took an ensemble of very cold atoms. So now it's an ensemble of atoms, right, 10 to the 6, 10 to the 7. And they tried to excite them to a particular Rydberg state. And they were operating close to this first resonance, for which the interaction energy is 1 over r cubed, and for which you can have an exchange of the internal state driven by the dipole-dipole coupling. So basically, those two atoms close by, P and E, could, due to this degeneracy at the first resonance, be transformed by the dipole-dipole interaction in the S plus another S state. In which case they have now a new S state, and these are actually also in degeneracy with this exchange mechanism, and then this S and S prime excitation in the system started to diffuse across the cloud. But what makes the system very particular and peculiar is the fact that because the atoms are frozen because they are so cold, this diffusion happened on a time scale which is much faster than the motion of the atoms. And in this way, and I'm bypassing a few arguments obviously here, you could correlate all the atoms of the sample, just because the excitation which kind of correlate the atoms with each other diffuse faster than the motion could erase these correlations. So, now what I want to tell you is a kind of new tool that was suggested around 2000, which is called the River Blockade, and which allow people to think in a new way about this Rydberg interaction for this quantum engineering thing. So, let's take two atoms, A and B. So it looks like a dream experiment, but now we do this dream experiment in the lab. These two atoms can be considered as two-level systems for any practical purposes. So you drive this transition with a laser, which has a Rabi frequency omega. It can be either in the ground state or it can be in the Rydberg state. The excitation has a line width, which most of the time is the Rabi oscillation, but not always. I will give you an example. And now what I want to look at is the spectrum of the two-atom system. So I have 4 possible states. Either the two atoms are in the ground state, or one of the two atoms is excited, I don't know which one, or the two atoms are in the Rydberg state. If the atoms are very far from each other, obviously those two transitions here, coupling one excitation to the second excitation, has the same energy. But now, because of this very huge dipole-dipole interaction when they are both in the Rydberg state, I see this 1 over R6 dependency. So basically this upper state here is shifted. The consequence of that is that if I try to excite one atom, basically I tune the laser on this first transition, which is the same as this one, then I am out of resonance with the second transition. So I've blockaded, because of the dipole-dipole interaction, which here is a van der Waals interaction, I've blockaded the excitation of two atoms at the same time. Why is it important? It's important for the following reason, which is that if you have your laser beam acting on the two atoms at the same time, and you don't know which of the two atoms you have excited, you have to add, in the quantum mechanical sense, the amplitude for having excited the first or the second. So the state you end up with is immediately an entangled state, which is exactly what Alain was discussing in his talk. So you see that this blockade is a way to engineer at will many-body state, because this is kind of the most trivial, in a sense, many-body state, although obviously it's not as trivial as it seems, as Alain has convinced us. Alright, so now there is a second appealing feature, but the thing is the fact that now the coupling constant between the ground state and this collective state here is enhanced by a factor square root of 2, which is kind of easy to see, because now the two atoms being in an entangled state cannot be think independently of each other, and so they act as a collective dipole. So if I measure what is the dipole of this two-atom system, I find out that this is enhanced by a factor square root of 2. Okay? Okay, so now, second important concept here for the blockade is the concept of blockage sphere, which I will discuss a lot during this talk, which is the following. So now I want to know what is the distance at which this blockade occurs. So this is kind of easy to see. What it's telling me is that if the atoms are closer than a distance which is RB, which I will give you in a minute, then I cannot excite the pair of two atoms. How do I define this blockade radius? Just by saying that the line width of the excitation has to be smaller than the van der Waals interaction. Then in this case, the interaction dominates over the excitation, and in this case, that gives me the Rydberg blockade. So what is important to realize is that for any atom which is within this sphere RB with respect to the first Rydberg atoms, there is no excitation which is possible. They are all blockaded. Okay, so I will use that extensively later. So just to give you a few numbers, if you look at the coherent excitation for which the line width of the laser is precisely the Rabi frequency, in this case, for typical Rydberg state that we can achieve in the lab, you find out that the blockade radius is on the order of 10 microns. So that's huge. It means that you have two atoms separated by the size of a virus or a microbe, and you can control really the interaction of one with respect to the other in the lab at a distance length which is actually very large. Okay, so now the consequence, and I'm kind of jumping here, there would be a lot to say, but this argument which I've done with only 2 particles could be repeated with n particles, in which case what you see is that you can couple in a coherent way with the square root of n enhancement of the Rabi frequency, this collective many-body state where all the atoms are in the ground state, so it's a kind of trivial many-body state, to this many-body state here, which contains only one excitation, but that's an excitation which is shared among all the partners within a blockade sphere. So that's a many-body state, really, in the sense of many bodies. So that's an entangled state, which is called, by the way, a W state, a Werner state. And I think that Serge discussed that a bit this morning. Okay, so now let me move on the demonstration of the fact that we can do that in the lab by trying to isolate 2 atoms in 2 optical dipole traps and demonstrate the blockade. So the first ingredient that I need here is how do we trap individual atoms in optical dipole traps. This was actually kind of a byproduct of the whole development of laser cooling and trapping that was going on, and especially in Paris actually, in the 80s and 90s, and that's, in a nutshell, the idea that we're using here is the fact that if I shine a laser on a 2-level atom, and that this laser is not resonant with the transition, basically the ground state is downshifted. We have to use a bit special optics, and at the end of the day we are operating at a diffraction limit, roughly the size of the wavelength of the light, and we want a trap which is as confining as possible because we want to be able to confine the atom in a volume as precise as possible. And typically the trapping volume is less than 1 micron cube. The thing here is that we need to use cold atoms just because the depth of the trap we can produce is on the order of a few millikelvin. So we need to start from laser cold atoms, and that's what we do. So around this trapping region, we use the usual tricks of laser cooling and trapping, so you have to believe me here, which is that you can cool the atoms down to 100 microkelvin. You have a reservoir of atoms, 10 to the 6 atoms typically, and from this reservoir you can load the atoms in the dipole trap. What is interesting about this configuration here is the fact that now the lasers that are ensuring the cooling are almost resonant with the atoms, so they scatter, the atom scatters photons. These photons I collect using the same lens, using a dichroic mirror, and sending that onto a photon counter. So this kind of configuration is very nice to observe the trapping of individual atoms, and that was actually demonstrated for the first time by Philippe Grangier and his team at the Institut d'Optique around 2000. So the loading of this trap has the following feature. The first feature is that obviously you've got the trapping region, you've got the cold atoms around, and you've got the cooling beams. One atom will enter the trap and will be slowed down in the dipole trap due to the cooling force, cooling action of these lasers. Okay, so they are slowed down, otherwise it's a conservative potential, so you need to have some dissipation in. Second ingredient is the fact that if now a second atom tries to enter in the trap, this cooling laser induces a loss, which is almost instantaneous. So basically there is a light-induced collision, which is all the more large that it varies as the inverse of the trap size. So that's the reason why having a very small trap size induces losses that are extremely quick and rapid. So now if the loss rate is much larger than the loading rate, you are in a configuration where you have either a 0 atom, or 1 atom which enter in the trap, or no atom because the second one has tried to enter the trap and you have lost the 2 of them at the same time. So what you can see is on the photon counter as a function of time, you can see these dynamics. So that's as a function of time the number of counts coming from the trapping region that we collect on a photon counter. So what you observe is that there are basically 2 levels. A low level, which is the background level of the experiment, and a high level, which corresponds to the presence of 1 atom in the dipole trap. And so the way we interpret that is that on the rising edge, 1 atom enters, is slowed down in the dipole trap and stays there. Then it stays there for some seconds here, and at the end, a second atom tries to enter, and you lose the 2 of them immediately, almost immediately. Okay, so this is a non-deterministic single atom source, but still is useful. It is useful because in a sense that's an heralded single atom source. So there is a signal. You don't know when the atoms is going to enter in the trap, but as soon as it's here, the atoms say, hello, I'm here, this is my signal, so you can start the experiment triggered on the presence of one atom in the trap. All right, so the second ingredient that I need to discuss is how we experimentally in the lab excite the atoms to the Rydberg state. And so Alan was saying that for his single photon source, he was using what had just been invented at the time, which is a two-photon excitation. We use that and in a very well-controlled manner, because now there is a lot of experience on this two-photon transition. We start from the atoms in the ground state, and we want to excite them to Rydberg state. So we have a laser, two lasers in stage, detuned with respect to intermediate stage, in such a way that we can have reduced this system to an effective two-level system between G and R. All right, so now, and I won't put too much emphasis on that because Serge discussed that this morning, but the idea now is that if you start with the atoms in the ground state and let this laser act for a certain given amount of time, you prepare a superposition of the atoms in the ground state or in the Rydberg state. Okay, so this is called the Rabi oscillation, as you probably all know. Now, there is something here which also Serge mentioned this morning, which is very specific to the fact that we are operating with individual particles, is that a single measurement on a single quantum object doesn't give you any information about the state of the object before you've done the measurement. You need to repeat the experiment many times in order to reconstruct the probability of having been instead in G or in R. So here what we're interested in is the probability to have excited the atoms to the Rydberg state. So that's the kind of curve that we get when we vary the duration of the excitation. Each point here is the repetition of 100 sequence of the same excitation procedure for a given time. So the way we understand this curve, that's a Rabi oscillation, which is basically the sine square here. We start with the atom in the ground state, and after some time we can excite them in the Rydberg state. Obviously it's not one, because that's a real experiment, and I don't need to tell you that real experiments are far from being ideal. All right, so now let's try to do that and to use the two tools that I showed you, which is basically trapping individual atoms and exciting them to the Rydberg state, to demonstrate this River Blockade with just two atoms. So with two atoms, so this kind of an idealized situation, because obviously they are trapped in some dipole traps that I don't show here. And what we're doing now, and that's an experiment that was done at the University of Wisconsin in 2009, so in the US, we are trying to excite one of the two atoms to the Rydberg state when the other one is in the ground state. So nothing particularly fancy happens. You see the Rabi oscillation, exactly the one I showed you before, as if there were no atoms in the trap A. Now you repeat exactly the same experiment, namely trying to excite the atom in state, the atom B, sorry, but the first atom A has been prepared by an extra laser in state R. And what you see here, that there is almost no excitation of the atoms to the Rydberg state. Okay, the fact that this is flat tells you that I cannot excite this state, which is the signature of the blockade. One atom is excited, I try to excite the second one, it just doesn't work, okay, because of the Rydberg blockade. So in a sense, what we are having here is a conditional operation, which is to say that the excitation of atom A is conditioned by the state of atom, the excitation of atom B is conditioned by the state of atom A, which is exactly the kind of logic that you want to build logic gate for quantum information. And actually this group, and I won't detail that, you can find in the note a few details, has used this blockade to demonstrate what is called a control knot operation that was briefly mentioned this morning, and also to entangle two atoms. Second experiment that was done at the same time, so it was in our group this time, is to observe the blockade and also this collective excitation with the square root of 2 enhancement that I was mentioning. So how does it work? So we just start with one atom, as I showed you before. We see the Rabi oscillation when we turn on the laser, and we repeat the very same experiment, but now we have two atoms that are present. And we measure the probability to excite the two atoms at the same time. We have this flat line here. Okay, which is basically, we say, well, that's the blockade. You obviously know as an experimentalist that when there is a line which doesn't take off from zero, there are many ways to do that, like switching one of the lasers off or putting a card in front of one of the lasers. So you want to make sure that on the very same set of data, something is indeed happening. And something does happen, because if I measure what is the probability to having excite one and only one of the two atoms, I have this curve. So basically that's the same run, and for each point we measure those three probabilities at the same time, and you do see that something oscillates, which is the probability to excite only one of the two atoms. The nice feature of this thing, obviously, is the fact that this oscillation occurs at a frequency which is square root of 2 faster than what it would be for an individual atom alone, far from any other thing. So basically the way you should understand this curve is exactly the generation of an entangled state. In a way, you start with the two atom state, which is with the two atoms in the ground state, you end up with a two atom state, which is the entangled state, having excited with the same probability, either the first one or the second one. All right. So now we can do a bit better than that now actually, and use a situation, work in a situation where actually instead of being fully in the blockade region, we are now in a region where the line width of the excitation is on the same order as the interaction energy. Why is it useful to do that? Because now the dynamics of these elementary many-body systems, that are just two particles, is a little bit non-trivial in the sense that you will have a superposition of having ground state, entangled state, and two atom excitation. But very importantly, the dynamics of this system is governed by two frequencies. The Rabi frequency, as before, because that's the drive from the laser, but also the second frequency in the problem, which is the interaction energy between the two atoms. So this is the solution of the Schrodinger equation for these three-state system. So that's something you can run on a computer very easily. So you see that the probability to excite this doubly excited state had this kind of very bizarre behavior. But at the end of the day, the underlying frequencies are only two. They are like the frequency, the Rabi frequency and the interaction energy. So let's move to the experiment. So we try to do exactly that. So we can vary the distance between the two atoms from 4 microns or 4 microns to 15 microns. And this is the set of data that we got. So we've got heaps of this data, but basically we can explore two intermediate cases. The case where you've got the blockade, which is exactly the one I showed you before, which shows here on the second column the probability to excite the two atoms at the same time, and here the probability to excite only one of the two atoms. So those two curves are the one I've already showed you. So I cannot excite two atoms at the same time. I can excite one of the two atoms, but with the square root of 2 enhancement of the oscillation frequency. Now we can work in the opposite regime where the atoms are so far from each other that there is no blockade operating. In this case, you do excite the two-atom system, and so basically you see this kind of oscillations, which has a shape that we understand. Very interestingly, between those two extreme situations, you have the interesting case that actually looks very much like what I showed you before. This is the solution of the Schrodinger equation. This is what we get in the lab, where we try to do that with exactly two atoms. So we've got a set of this data, and we can fit the data that I just showed you, this oscillation, the dynamics of these two very simple many-body system, and we can extract from that the interaction energy between two atoms. So what we see here is the interaction energy as a function of the distance between the particles in log-log scales, to emphasize the fact that this is a power law, as a function of for different principal quantum number. So you already see here some kind of wild scaling, the n to the power 11 that I was referring to. Because if you look at a given distance and you just change by a factor from 53 to 62, so that's only a minor change, a relative change in the principal quantum number, you enhance the interaction energy by a factor of 50. So it's pretty dramatic scaling. The second thing is that obviously you want to compare that with theory, which we know from the 1930s, which is the van der Waals interaction, and that's the kind of agreement we got between the data and the experiment. So obviously I'm not pretending here that this is a discovery about the van der Waals interaction. That's just showing that in the lab we can handle those very tiny and elementary systems well enough to be able to see in a very pristine environment and very pristine condition the interaction energy between two atoms. All right, so let me move on briefly to the case of, we jump directly, we've done it for two atoms. I will show you what people have observed in small atomic ensemble. Small atomic ensemble, still cold, but now containing 10 to the 6, 10 to the 7 atoms. And people wanted obviously to observe also some evidence of this Rydberg blockade. So the first experiment that was done was in 2004, was trying to send a laser, which this time is a single laser, it doesn't matter, on this, trying to excite the atoms to the Rydberg state and to measure the number of atoms that were excited. So if everything goes with no interaction happening between the atoms, you expect that the number of Rydberg atoms that you produce is directly proportional to the intensity of the laser. And instead, what they observed is the following thing. So that's the fraction of atoms promoted to the Rydberg state as a function of the intensity of the laser. If you do that for low principal quantum number, which is to say low interaction energy, basically the scaling here is roughly correct, just because the interactions are too weak to induce some blockade. Now you repeat that, but for an increasing principal quantum number, in which case you drive different type of interactions, and in this case you can observe kind of a saturation of the number of Rydbergs that are produced. How do you interpret this? Well, the blockage sphere that I have introduced is a very useful picture, because it tells you that as soon as one atom has been excited to a Rydberg state, it completely blocks all the surrounding atoms in such a way that I cannot excite a second atom here. So in any case, I'm kind of expecting of a saturation of the number of Rydberg atoms that are produced, and this saturation, the maximum number, is just the volume of the sample divided by the volume of the blockage sphere. So this group couldn't really observe the full saturation curve, but another group in Germany was able to see it. So basically that's a group where they were using a much denser cloud and also a more coherent excitation. And the idea is that they could observe here this saturation of the number of Rydberg atoms, so in full agreement with this idea of blockage sphere. There is a bit subtlety here, though, is that I told you that if you couple to a many-body system, you should have a square root of n enhancement in a Rabi oscillation. And obviously, there is no Rabi oscillation here. But the reason for that is because the blockage sphere is smaller than the size of the sample. Okay, so because of that, it means that within each of these blockage sphere, I have an inhomogeneous distribution of n. So very much like the kind of thing that Serge Haroche and Jean-Michel Raymond have seen with photons coupled, atoms coupled to coherent field in a cavity. What you need to do is to sum in an incoherent way all the Rabi oscillation that are many-body Rabi oscillation in all blockaded sphere. And because this is inhomogeneous, it looks like at the end kind of an incoherent behavior. So once again, exactly the same physics over and over again in the case of Serge, in our case for two atoms, in the case of multi-atom thing. So it just shows you the nice unity of this field. So just to finish off on this collective oscillation, what I want to show you here is that recently these oscillations have been really seen in a sample for which the size is actually much smaller than the blockade radius. So basically, just by increasing the number of atoms, they could see some Rabi oscillation, so that is square root of n Rabi oscillation, with an enhanced Rabi frequency when you increase the number of atoms in the blockaded volume. And they could show that actually this square root of n scaling is kind of accurate. All right, so now what I want to move on is the last application, which is trying to show you that people can do something, so to speak, useful beyond just the mere demonstration of the blockade. And so that's a field which is very rapidly developing, which is to use this Rydberg blockade for quantum optics task. So let me just briefly tell you a few things about quantum optics and quantum information. So people are, despite the fact we are still at the basics of what we can do in the lab, people are already dreaming of a quantum internet, which is basically a huge ensemble of quantum systems coupled to each other by fibers, and in these fibers you would have entangled photons floating around and connecting all those sides. So basically, to put it a bit differently, you would interconnect quantum processors, so those blue boxes, with some kind of quantum memories where you would store the quantum information, and the natural carrier of the information in this case would be a photon, because that's the thing that can travel far and quick from one place to another. So obviously that's kind of a dream at the moment, but actually progress are very steady and very impressive in the lab. But in order to do that, there are essentially three things that you need to do. The first one is you need to be able to produce individual photons on demand. So you have to believe me here, but that's one of the requirements. Second requirement, if you want to have quantum memories, you need to be able to store photon in one of these small boxes here, just because, in the meantime, you're operating on a different box. So it's called a quantum memory. And third, very importantly, you need to have a photonic gate, so something which allows two photons to interact with each other, but the state of one photon being conditioned by the state of the second photon. An example of here would be basically, you've got one target photon, one control photon, and the state of the target, let's say the phase of the photon, whatever that means, would be affected by the state of the control photon. So what it requires is an interaction between photons, and obviously we know how to do that. We know that nonlinear optics can make photons interact, but the problem is that for most nonlinear medium, this interaction cannot be made efficient at an individual photon level. So the trick here is trying to extend and to use the blockade in order to demonstrate some nonlinearity at an individual photon level. So we are not completely there yet, but there are some steady progress, as I will show you in a minute. So the first thing that I want to show you, which has been done over the last 2 years basically, is to use the Rydberg blockade in a small ensemble to generate individual photons. How does it work? You just prepare an ensemble all within the Rydberg blockade radius, prepare all the atoms in the ground state, shine light on this system, in which case you create a Rydberg excitation, and now with a second laser you bring the system back to this intermediate state, and from here it's going to decay. Very importantly, because you need to ensure in this 4-wave mixing process momentum conservation, then you find out that the momentum of the exiting photon, this one, is actually along the momentum of this laser here. So you on top of that know in which mode the photon is going, which is very important for applications. Something which people have demonstrated in the lab is this kind of curve. So that's not the most beautiful, but that's the first demonstration. They show that the probability to get 2 photons at the same time coming out of this system was highly reduced, which is the signature that you only have you have less than 1 photon coming out. Okay? Because basically if you had some Poissonian statistics, you would have this, which would be equal to 1, like an attenuated laser beam. So the fact that it's attenuated tells you there is a non-classical quantum state of light here, which is close to a single photon state. The group which demonstrated that could also demonstrate the principle of the storage, because now, while the atom is in the excited state, which is to say you have 1 photon, it is absorbed, stored in the atom, you can store it in an intermediate state for a given time, and then bring it back to here and read it out. So it's kind of the principle of a quantum storage that people have demonstrated early this year. And the last thing that I want to discuss, so that's my last example, is the nonlinearity at the single photon level, but here I need to introduce a second non-necessarily very intuitive mechanism, which is called electromagnetically induced transparency, which I will mix with the Rydberg blockade at the end. So the idea is the following. Just take a 3-level system here, and let's concentrate for the time being on the 2 first ground state. If I shine a probe on this system, the atoms are going to absorb the light and scatter the light off the laser beam, in which case I have a transmission here, so the transmission, which is attenuated just because it's absorption. It's absorbed because the light is scattered in a different direction. It turns out that there is a configuration where if you add here what is called a control laser, you can switch off the decay from this intermediate state. In which case, this transmission is fully recovered. So basically, any subsequent photon in the laser going through would actually go through without any attenuation. So in this way, you control the transmission of the system just by adding or not the control laser. And now we can combine that with the Rydberg blockade. And so that's what people have done very recently in the lab. So you start with an ensemble of atoms. So I just assume I have 2 atoms nearby. It doesn't matter. So this second atom is one of the atoms of this thing, and this one is a particular atom. The first thing I do is just I prepare the atoms in the ground state. I excite by sending 1 photon on the probe being in this EIT thing. So 1 photon goes through. When it goes through, all the states of all the other atoms are shifted around because of the Rydberg blockade. And then when the photon goes back down to the ground state, then all the states go back to their initial position. But now if you do the very same thing, which is that you have 1 photon in the medium, which has shifted all the levels around, and you send at the same time a second photon, these photons will not be in the EIT condition because this laser is out of resonance. Therefore, the scattering will indeed happen. And in this way, you scatter the second photon away from the direction of the first one. So this is a way, by combining the Rydberg blockade with this EIT mechanism, to control with only 1 photon whether the second photon is transmitted or not, which is exactly the kind of nonlinearity you want at the single photon level. And so people have shown that in the lab very recently. So they show this is exactly this transparency window that I was showing. So the transmission as a function of the probability tuning, so exactly the curve that you had here. In the IIT condition, so basically no control field apply. And now you apply the strong control field, in which case what you have, you create more and more Rydberg atoms. So you kill the EIT condition, so you recover the transmission. So that's kind of the underlying proof that there is this nonlinearity at the single photon level. And people have done actually a very nice experiment of showing that indeed they could order the photons while they go through the sample in the following way. If we go back to this picture here of having two photons, one going through, the second being scattered because not in the IT condition, what it is telling you is that the first photon prevents a second photon from going in the same mode during a time which is the size of this Rydberg blockade sphere divided by the velocity of the photon in the medium, which is the group velocity. And so in this case, what you have is this kind of curve. If you send a random distribution of photons through, at the output, you've got an ordered flux of photons. So this kind of medium where you combine EIT with Rydberg blockade is a photon ordering machine, if you want. All the other photons, which are not exactly at equidistance here, are actually sent away from the incoming beam. So that's exactly what you want. That's the underlying mechanism for a photonic gate. And the proof that this is indeed the case is on this curve, where they've measured the probability to find two photons at the output as a function of the relative time. So basically, if one photon is in the medium, just after, do I have a probability to have a second photon? And the answer is no, because this is a very low probability. And this time here is in agreement with this blockade sphere picture. So people have realized that, and now they need to put everything together to get a real photon source. All right, so now I'm done. I'm sorry, I've been just a bit long. So I'm done on the conclusion of this, on this interacting Rydberg gas. So basically, this is a very nice playground where you can, there's an interplay between very quantum argument, very semi-classical argument, where the Bohr model is kind of used on the daily discussions between people in the lab. And the basic demonstration, I would say, are completely okay. So where is this field going? It's going in mainly in two directions, so that's not very original, what Alan discussed in particular. So quantum information, but in order to really do some very useful quantum information task, all the experiment needs to improve the quality of what is called the fidelity of any operations. Second thing, second direction is to indeed try to simulate condensed matter system using this interacting Rydberg system. And as example, there are like spin systems where you can study quantum magnetism, which is still has a lot of open question. New phases of matter with some kind of tailored interaction, because you can play with electric field, microwave, and so on, and tailored interactions. And there are some old ideas that are coming back at the surface just because the technology is evolving, and people know how to do things that they were not able to do 50 years ago or even earlier, which is to try to couple this very large dipole system to a solid state system. So for example, do the kind of experiment that Serge and Jean-Michel had done, where you would replace the microwave cavity by just this microwave circuit here, and you would send a Rydberg beam through that. So people have already demonstrated, so last year, that they could at least drive a Rabi oscillation between this microwave system and the Rydberg atom. So that's the very beginning of this, but once again, this is using this very large polarizability, so of the Rydberg atom, which could also be used as an asset, for example, to probe the electric field at a surface. You could use that as a metrology instrument. And with that, I really would like to thank you for your attention.